This sea snail, called aplysia, is somewhat of a celebrity, at least in the world of memory research. It was this lowly snail that revolutionized the way neurobiologists, like David Glanzman, think of memory. But how do you give a snail a memory?
We're going to give it a few shocks, but don't worry, it's not going to harm the animal. It's not going to produce any long-term damage.
Wow.
Giving it electrical shocks teaches the aplysia that the world is a dangerous place. How do we know it's actually learned?
We look at a reflex.
Touch the siphon of an aplysia, and it triggers a defensive withdrawal reflex.
And I'm just going to touch the siphon like that. And there you see, that's the reflex.
This reflex can tell scientists if the snail has formed the memory.
The longer the gill and siphon remain retracted, that's an indication that it's learned what we taught it.
An aplysia that hasn't been given any shocks will respond with a short-lived contraction.
There it's out.
So what was that?
11 seconds.
All right.
But an aplysia that was taught to be on guard responds much differently.
Now there's the reflex. Now the point is that it stays tucked.
So this guy's on a high state of alert here.
Yeah. So you see the siphon's just starting to come out now. And at 45 seconds. So it's 4 times as long as the naive animal. And it's learned that there's a danger in its environment. That's what it's learned.
This learning is observed in its changed behavior, but scientists can also see signs of memory in aplysia's legendary brain. Let's just say this sea snail is neurologically well endowed.
It has very large, huge, some of the biggest neurons in the world.
Its few but gigantic neurons inspired researchers to essentially create an aplysia mini-brain out of a sensory neuron and a motor neuron.
We take those out of the animal and we put them into cell culture and they grow together, and then we have a mini circuit, a neural circuit.
Scientists can see, on a cellular level, what happens as the mini-brain forms a memory. So, what is happening?
Basically, we see 2 things. The synapse between the sensory neuron and the motor neuron gets stronger.
When the snail gets zapped with electricity, the neurons start communicating differently, sending more, stronger chemical signals and receiving more signals. This change, which can happen quite quickly but doesn't last forever, corresponds to short-term memory. But administer the shocks over a longer period of time, and the 2 neurons physically change as the snail learns.
Anatomically, we actually see the growth of new synaptic connections between the sensory and motor neuron.
And it's this physical change in the neurons that is long-term memory. As the snail learns over time, its brain is making more and more connections, so that even when the snail gets a break from the shocks, it will still remember them. Besides training sea snails to be on a high state of alert, the research on aplysia has been integral in understanding learning and memory, and not just for snails.
When you're looking at these changes in aplysia, you're basically looking at the bedrock of learning. Those same processes take place in our brains.
And with the advancements in memory research that aplysia has already inspired, it is most likely going to remain in the spotlight for decades to come.